My name is Paul Callaghan, and in this series of videos we're going to be looking at some of the basic ideas behind nuclear magnetic resonance and magnetic resonance imaging. And to help us look at those ideas, we've got this apparatus here behind me. It's a very simple nuclear magnetic resonance apparatus which can demonstrate most of the basic principles we need to understand in order to appreciate what magnetic resonance imaging and nuclear magnetic resonance can do. In thinking about magnetic resonance, we'll be thinking about atomic nuclei and their behaviour in a magnetic field. And I want to start by demonstrating some of the basic physics behind the behaviour of atomic nuclei in a magnetic field. And to help me do that, I've got a mechanical device, and it's this wheel over here. The first principle of understanding atomic nuclei in a magnetic field is to realise that those nuclei have magnetism. And so, like little compass needles, when they're placed in a magnetic field, they tend to line up with the field. And I can demonstrate that idea with this wheel. There's no magnetic field that's playing a role here, but we have the Earth's gravitational field. And the effect of that gravitational field is that if I try to suspend this wheel on a string like this, it twists and finds a natural orientation pointing along the Earth's gravitational field. Why is that? Well, the combination of the weight force of the wheel and the string causes a torque to act. And that torque or twisting force reorients the wheel so that it hangs vertically. The second idea that's really important in understanding nuclear magnetism is the idea that the nuclei themselves have angular momentum. Let me demonstrate angular momentum with this wheel. I can do that simply by spinning it. Now let's try that same trick of suspending the wheel, like I did before, on the string, now that the wheel is spinning. Something really remarkable happens. That effect is called precession. And that precession idea is very, very important in understanding the way magnetic resonance works. Let's look at that precession a little more closely and see how it depends on the orientation of the axle of the wheel. I'm going to start with the wheel with its axis horizontal. It takes about a second to go around. What happens if we orient the axle slightly differently, like this for example? It takes about a second to go around. In fact, it doesn't matter what orientation we have this axle, the precession frequency is pretty much the same. However, if we do suspend the wheel in that natural low energy position, the precession is very, very hard to see. If we tilt it a bit, it reappears. So we have to have the axle of the wheel tilted from the vertical in order to see the precession. By the way, there's another position where the precession is very hard to see as well, and that's with the axle pointing up like this. But anywhere in between, pointing up and pointing down, the precession is very visible. By the way, these two states of pointing down, pointing up, turn out to be very relevant in the case of the atomic nuclei that we'll be looking at in these series of videos, and that's the hydrogen nucleus. It turns out that the hydrogen nucleus has two very natural states in a magnetic field, one pointing one direction and one pointing in the other direction. So what have we learned here? We've seen that in order to observe the precession, we need to have the axle tilted at some angle away from the vertical. And that begs the question, if we did start in that low energy position with the axle pointing vertically downwards, how could we disturb it in such a way that we could make the precession visible? And I want to demonstrate that to you. Just watch this trick. I did it. I used my finger to apply a torque to the wheel that brought the axle away from the vertical position into the horizontal. What was the basic idea behind the trick? The first thing is that I had to apply the torque in the horizontal plane. I had to apply it in a direction normal to, or at right angles to, the torque that the Earth's gravitational field is applying. The second thing is that I had to move my finger around in synchrony with the wheel, keeping the reorientation of that torque from my finger at the same frequency as the precession frequency. Let me just demonstrate that again. So this movement of the torque following exactly the precession frequency of the wheel is known as resonance. The frequency is exactly the same in both cases. And the idea of resonance is really central to what we'll be looking at when we reorient atomic nuclei from their natural equilibrium states in a magnetic field. So that's wheel mechanical resonance. When we perform nuclear magnetic resonance, we have to do the same trick. We have to apply a torque that's orthogonal to the torque of the magnetic field on the spins, and we have to have that torque varying with time or oscillating in exact frequency match with the natural precession frequency of the nuclear spins. And how do we apply that torque? We do it with another magnetic field. A magnetic field that's orthogonal to the main magnetic field that tries to orient the spins, and a magnetic field that's oscillating in time in exact synchrony with the precession frequency of the atomic nuclei. And that is nuclear magnetic resonance. There's one more thing I want to show you. Let's go back to the wheel. Suppose we do this wheel mechanical resonance and end up with the axle pointing in a direction that really shows the precession very nicely. The horizontal orientation as shown here. Let's look what happens with time. Gradually the wheel reorients and the visibility of the precession starts to die away. This returning to some sort of equilibrium is something we'll also see happening with atomic nuclei. In this video, we're going to be moving from the world of the wheel to the quantum world of the atomic nucleus. And to help us develop some ideas behind the quantum behaviour of atomic nuclei, I prepared some slides here, which we'll go through in turn. I'd hate you to think that this is what an atomic nucleus looks like, but we need to use some symbol to represent our nucleus, and a blue ball is as good as anything. A blue ball with a vector to represent the direction of the angular momentum and the magnetism. And in a magnetic field, the lowest energy state is with the magnetic dipole of the nucleus aligned with the magnetic field direction. We use the words spin or angular momentum and magnetic dipole moment interchangeably when it comes to direction. In this set of videos, we'll be exclusively concerned with the hydrogen nucleus known as the proton. It has two possible quantum states in the presence of a magnetic field, spin up and spin down. We've seen spin up already, it's the low energy state. Spin down is the high energy state. And in general, what I want to do in this set of slides is to introduce the idea of what happens when we have lots and lots of nuclei in thermal equilibrium with a magnetic field. First, we need the idea of temperature, and we use a little thermometer symbol on the bottom right to indicate temperature. So let's look at what happens at finite temperature. Thermal energy means that not all nuclei will be in their low energy state. In fact, there's a proportion in both the high and low energy states, with a preponderance in the lower energy state. Note that these thermal equilibrium states are not superposition states. Each nucleus is definitely in either up or down states, but there is a slight preponderance of up, the lower energy state. The ratio of populations in each state is given by the Boltzmann factor, which in turn depends on the ratio of the thermal to the magnetic energy. At room temperature in laboratory magnetic fields, the thermal energy is much greater than the magnetic energy, so that means the populations are nearly equal. However, that slight preponderance in the lower energy state shows up as a spin excess. It's the spin excess that's visible. All the remaining spins cancel out their angular momentum and magnetism and are invisible in nuclear magnetic resonance. We can increase the spin excess by lowering the thermal energy, in other words, by reducing the temperature. At absolute zero, all the spins will be in the low energy state and the spin excess will be at its maximum. But that's not too practical for many samples, humans undergoing an MRI scan, for example. But we do see that the magnetisation vector grows as the spin excess in the low energy state grows. Let's go back to room temperature. There we are with a small spin excess again. But another way to increase the spin excess is to keep the temperature fixed and increase the field. This way we increase the magnetic energy while the thermal energy remains fixed. Here we're going from 2 Teslas to 9 Teslas and then back down again. But even if we're restricted to weak fields and room temperature and our spin excess is very small, remember that there are vast numbers of nuclei in our sample, and even if only a small fraction are in the spin excess, the total number could be quite large. So let's take our thermal equilibrium magnetisation and see what we can do using the nuclear magnetic resonance trick. Just like our wheel in its low energy state, where precession was invisible, we have the magnetisation pointed along the vertical axis, and we need to reorient the nuclei. Once we do that, the precession will be visible. We call this precession after the physicist who first predicted it. It's called the Larmor precession, and the frequency of precession is known as the Larmor frequency. Note on the top right-hand part of the slide the equation which tells us the precession frequency. It's the most important equation in NMR and MRI. It says that the precession frequency is proportional to the field, and the constant of proportionality, gamma, depends upon the nature of the nucleus. That gamma is sometimes called the gyromagnetic ratio or the magnetogyric ratio. Hydrogen nuclei have the biggest gamma and are the most sensitive nuclei to be used for NMR and MRI. Finally, note the use of a coil to pick up the induced voltage from the precessing spins. This constitutes our free induction decay signal in NMR. Let's summarise some important ideas from these slides. First of all, the strength of the magnetic field determines the amount of magnetisation that we have when the atomic nuclei are in thermal equilibrium. Second, the strength of the magnetic field also determines the precession frequency of the atomic nuclei. The higher the field, the higher the precession frequency. And the third idea we see is that we need to have a coil that's used to produce an oscillating magnetic field in resonance with the nuclei that causes that torque which tips the magnetisation out of equilibrium into the transverse plane. The same way that with the wheel I used an applied transverse torque moving around with the precession of the wheel to reorient it. And that same coil is used not only to transmit to the nuclei but also to receive the signal, to pick up that electromotive force, that oscillating voltage, as the nuclear magnetisation precesses around in the coil, with the signal gradually decaying away with time as the spins come back to thermal equilibrium, and we call that signal which decays with time the free induction decay. And that's this one. This is a very complicated looking coil. It's got lots of layers and it's got some very ingenious patterns in the windings. What this coil does is to produce a magnetic field that varies in 3 orthogonal directions. And these varying fields are known as magnetic field gradients. The use of these coils is that they lie at the heart of magnetic resonance imaging. By varying the magnetic field in 3 orthogonal directions, we can produce a Larmor frequency that depends upon position. And that's the basic principle behind MRI. We'll be looking at that in a later video. In this video, we're going to be looking at magnetic resonance imaging. And we're going to carry out one of the simplest imaging experiments possible on a very simple sample comprising these 2 tubes of water. Remember that the Larmor precession frequency of the nuclear spins depends upon the strength of the magnetic field. Now just imagine if we could make the magnetic field higher on the top tube and lower on the bottom tube. That would mean that the top tube would have a higher frequency and the bottom tube would have a lower frequency. And if we looked at the spectrum of that, we should see 2 signals at 2 different frequencies corresponding to the 2 tubes of water. Now imagine if we could make that magnetic field vary linearly along the axis where the 2 tubes are separated. In that case, we'd have a very simple relationship between frequency and position. In fact, our frequency axis would also be a position axis. How could we do that? Well, we have the gradient coils. These are the coils that are inside the probe of the Terra Nova apparatus. And these coils are able to produce a variation of the magnetic field along the vertical direction, varying along each of 3 orthogonal directions, along the X, Y, and Z direction. In this